excited to be here today, guys. Again, my name is Val Laguna, and I work in Taylor Station plant for Procter & Gamble here in Martinsburg, West Virginia. To give you a little bit of my background, I'm originally from Venezuela in South America. I moved to the United States when I was 10 years old. I grew up in Florida. I moved to Chicago, graduated high school in Chicago between 10th and 11th grade. I moved out there. Went to University of Illinois, where I got my mechanical engineering degree. And after 3 successful summer internships at Procter & Gamble, that's where I started full-time in Kansas City. I started as a process engineer, which is a little bit of what we'll talk today. I also got to do a line leader role, worked in our material process delivery group, and now, as mentioned, I'm the dish making senior manager, so I'm a department leader here at Procter & Gamble. All right, so where did my interest come from? Really, it was all about manufacturing. When I was 8 years old, I got to see a manufacturing plant, and I thought it'd be the coolest thing ever. How It's Made quickly became one of my favorite TV shows. And my parents told me, hey, you want to work in manufacturing? Engineering is a great way to do that. So, manufacturing. What exactly do I want to manufacture? Lots of options out there. Things like electronics, airplanes, medicine, machines, and then there's also things like material movements. And all of these things tie into different types of engineering, like aerospace engineering, industrial engineering, civil engineering, depending on what you want to do. What's really cool about engineering and what's cool about manufacturing, what I learned early on is realistically you need every type of engineer to do everything. So I could grab that airplane picture and put it under pretty much any of these engineering types, because you need your material engineer is going to help you with the new carbon that you're using for the outer shell of the plane that makes the plane lighter. When you're talking about materials, if you're looking at materials, your biomedical engineer might need a very unique material that fits and gets along with the human body. When you're talking about electronics, you might need a very unique chemical reaction to be able to put these tiny components into a microchip. So it's super diverse, it's super cross-discipline, and there are a lot of options out there. And as I look through all of them, I wanted to do something really broad, and mechanical engineering is what worked for me, because it seemed like no matter what industry you went into, you needed a mechanical engineer. I later learned that no matter what industry you go into, you need pretty much every type of engineer. But I really like how tangible mechanical engineering was, the fact that you could see what you were doing most of the time, and to me it felt like it made a lot of sense and that there were a lot of options. So that was my path on how I picked engineering and how I specifically picked mechanical engineering. And after 4 years at 4.5, actually have to take that victory lap. After 4.5 years at the University of Illinois, I started with P&G full time. So here's some pictures of my career at P&G. I've worked both on the packing side of the technology and the making side of the technology. So you can see, going into our filler to check, to do testing, looking at our HMI screens as we're monitoring our process, fixing pumps, unloading trucks, as well as working on labeling issues, working on bottling issues. So it's really been a ton of fun. It's been really diverse. And kind of one of the bonuses of P&G is we also do a lot with affinity teams. So here you have a picture of our women's network. Here you have a picture of some of our affinity team leaders. So it's really been an awesome career. So to talk a little bit about why P&G and what I've gotten at P&G, huge company. And I talked about one of the reasons that I wanted to go into mechanical engineering is because it felt tangible. Well, consumer goods are even more tangible because the things we make, you see on the shelf at Target, Walmart, grocery stores. We make things on the line. Sometimes there are things that are brand new, maybe a new formula or a new bottle type, and you see it being made and you understand all the effort that went into it, and then you get to see it on a shelf and you can tell your friends and family about it, and it's something that people can relate to, right? So I thought consumer goods were going to be really fun, a really good fit, and that was one of the reasons that I got attracted to P&G. I love manufacturing. I had my mechanical engineering degree, and it just made sense for me to go do something that I could see and really feel, and I used every day and could relate to. So I went into with P&G. We are a 185-year-old company, really founded on purpose, values, and principles, and having really strong values. Another thing that I really, really like. So it feels like the people I work with are always trying to do the right thing and are trying to build those values in me and are encouraging me to do the right thing. So it's a really great environment. So to talk a little bit more about what exactly I've done within P&G, and I know one of the intents is, what does your job look like? What do you actually do? So I'm going to talk very quickly about 3 of the roles I had. So one of them was a process engineer, and really it's all about executing process improvements. So making things run better. So how did we do that, right? We first and foremost established base condition. So what does it look like when it's perfect, when it's okay? Like, how do I know that this piece of equipment is in the condition it's supposed to be in to run what it needs to run? Huge part of it, right? Because you go up to a piece of equipment and actually being able to say, you know what, that's supposed to be higher, lower, wider, narrower. There's too much wiggle here, you know? We also worked with project startups. So sometimes whatever you have isn't good enough, or you're making a change and you need to make it better. So we work with the engineering teams, or what we call the engineering teams. They're, you know, everybody's still an engineer, but they're bringing in like new pieces of equipment. And we want to make sure that those pieces of equipment integrate seamlessly with what we have today. And then the other part of it is loss elimination. That's what you're going to hear me talk about the most. And it's my favorite part of my job and part of being in engineering, which is that you have a loss, you have something that's not working how it's supposed to work, and you want to make it better. You want to improve it, right? The other role I'll talk about is I was the line leader. So one of the really cool things about engineering is it really makes you qualified to go into a lot of different areas. So as a line leader, I was more on the manager side of the equation. And my job was to manage line reliability. And there's really 2 things that affect how well your line runs. How often it's down because you wanted it to be down, and how often it's down because you didn't want it to be down. So things like changing over, you plan to change over, but if you can change over quickly or quicker, that's going to help, you know, how much time you can run. Every day you make a plan to clean your equipment or do maintenance on your equipment. But again, if you can do maintenance less often because you have the right processes in place, then that's great. And again, these things all require kind of the problem solving, like how do I make it better? And then also decreasing unplanned downtime. So the line breaks and we're not planning for it to break. Well, how do we build capability so that people can see that it was about to break? How do we find the defects that would have told us that it was going to break? How do we build capability so that people know how to intervene and how to interact with the equipment effectively? And then another role I did, a material process delivery leader. I was a transformation expert. So essentially, we manage change. So things change, and we want to make sure that when we change them, we're still validated and we're still making good quality product. So we dealt with things like material qualifications, like, hey, I want to run this formula that I've ran before, but instead of putting blue dye in it, I want to put yellow dye in it. Or instead of putting perfume A, I want perfume B. Does that affect my ability to make the product? Material qualifications can also be like your corrugate. So, you know, if you guys see it in stores, corrugate's really, really common. Actually, you know, bottles made of plastic. What can we do to use less corrugate or to use less plastic and still give the consumer the experience that they deserve? Also validating process changes. Hey, right now I run this line at 100 bottles a minute. Is there any way I could run it at 120 bottles a minute? What would it take? You know, so you work with your process engineers, you work with your line leader to make sure you're not impacting their downtime. And then you say, okay, we're going to do these tests and I'm going to validate it and I'm going to confirm that what we're doing is good enough. And then there's the innovation execution piece that MPD also works on. And it's, hey, we're making this change. And I want to run a different type of bottle, or, hey, I want this brand new ingredient that we've never had before. And it's an innovation because we want to impact the market in some positive way. And as the transformation experts, we're the ones that can say, well, it's a great idea. Here are the risks, and here are the design improvements I need. And here's the help I need from my process engineer to go find new center lines. Here's the help I need from the line leader to go train the people on this capability. So that's some of the roles I did. And what's so great about my career so far is every role is contributing to this absolutely giant company that's, has 65 leading brands. We sell in over 180 countries, has a ton of nationalities. So I really get to collaborate all over the company, and it sets me up to be able to move to other parts of the company as well. So in my 8 years, I've had 4 roles, and it's really exciting that every 3 years or so, I get to try a new role and I get to do something new every 2 to 3 years. And I can also find where my passions are. Really enjoyed my process engineering role, really enjoyed my line leader role. I wanted to try something not as core in the operation, so I went into the NPD role. I learned a lot, but I also learned that my passion is more towards being on the floor and core operations and people dealing with the day-to-day, which is why I moved to the role I'm in now as a department manager. So I love how much you get to collaborate, and it really is just part of industry. And it's one of the benefits of working for a big company is that you can move around a lot, you get a lot of exposure, and you get a lot of options. We always say that you can switch careers without switching companies. All right, so one of the questions was, what do you do? Help me understand for my students what you do. So I'm going to focus on my process engineer role and some of the things that I did there. So again, process engineer, my role was to execute process improvements. What did my day look like? It's a role that's very, very daily driven, just to make sure that the operation is stable. And then you do spend some time working on some of the longer term losses. So first thing in the morning, we always had a daily results meeting. How did things go yesterday? All right, so based on how it went yesterday, here's the data that I'm going to go gather on the losses that we had. So I understand, hey, is there process changes I need to make? Is this loss that we had yesterday more or less important than some of the things I'm already working on? Then after you kind of know where your priorities are for the day, which is kind of the intent of the first 2 parts, you go do maybe some loss improvement testing, both immediate losses, so like the ones that just happened, or a chronic loss. Hey, we've been seeing this for months and months and months. And we know it's a problem, we've been trying to fix it, right? So I would literally spend my entire morning from the time I got into the plant, 50% of my time was spent, the way we like to call it is on the floor. So doing things like understanding what issues we have and trying to make those issues better, and spending time with the teams to understand what help they need, what are they seeing, and then to test things and things like that. So that's my morning. And then comes the afternoon. Generally, I might have like an engineering project meeting. Hey, there's this change coming. Let's talk about how it impacts your line, your area, and what kind of help you need, right? And then sometimes I get help requests from other areas of the company. They might say, hey, we're thinking of making this new formula, but the maximum temperature it can handle is this. Can you give me some historical data on what your temperature, on what your process set points have been for temperature, because we want to see if this formula would be a constraint or not, or whether we need to widen or winter or not. So I might try and get them some of that data. And then as I'm working through these losses and doing all these things and learning about the equipment and saying, hey, we need to execute this work process differently. We need to train differently. I'd spend some portion of my afternoon developing trainings or developing standards that are going to help the folks on the floor be able to address losses more quickly. And then also then spend some time on, okay, these are the losses that we've had for a really, really long time that I might have not actioned today specifically, but we're still trying to work on and make progress against. So I'll spend some time there, like with kind of any leftover time, really focusing on anything that's long-term. And then finally, we do some sort of reconnect or plan for the next day to make sure we're all on the same page. So that's kind of when my day went when I was a process engineer. And I like to give you some examples of some of the losses I experienced. But first, we're going to talk the biggest part of everything I've mentioned so far, whether it's a process engineer, line leader, and in that MPD role, it's really about problem solving. The types of problems you solve can be a little bit different. Like one could be equipment related, transformation related. It could be a work process, but no matter what, in order to solve problems, you're going to need some curiosity, some creativity, some critical thinking, and then strong foundations. Which to me, this also answers the question a little bit of what it takes to be an engineer, right? People always talk about, hey, really good math and science. Absolutely, that's very important. But as I'll show you in some of the examples, I purposely pick one or two that had math in them, but you'll notice that some of the other ones don't. They really require more the creativity, the curiosity, the critical thinking. And the strong foundations may be just understanding that part of the process really, really well. It doesn't mean you need some extremely complicated understanding of some theoretical math and science. Now, obviously the engineering curriculum is very math and science heavy, but I always like to encourage that if you have some passion for problem solving for these things, and you can get through that math and science piece, you know, nowadays with so many resources online and so many schools doing really strong mentoring programs and teaching programs and like office hours, you know, you really can get a lot of support to get through some of the math and science. I just don't think that should be a big discouragement for people. And then in general for problem solving, the way we problem solve is very similar to how most people solve problems every single day. We just ask a lot of W questions and a couple of H questions. So we ask, you know, what, when, where, and then we ask a lot of whys, you know, because you have kind of the immediate cause as to why something happened, but then you want to understand, well, why was that even a possibility? And why was that even a possibility? So you can get to your actual root cause. So for us, it's really about problem solving. All right. So now, some examples of problems that we've actually solved, that I've solved in my career as a process engineer. Trying to keep it relatively simple so that it's easy to digest. So one example, we had dented bottles detected on the line, which caused spill product not meeting quality requirements. So you can kind of see a little bit in some of the pictures, the caps look a little dirty. If the bottle is dented, I can't fit as much product in it. So immediate actions, we like inspected the equipment, inspected the incoming bottle pallets, and what we found is that we only had defects on the corner of the bottles, and we also didn't have the defect on all of our sizes. So when we looked into it, you can see some pictures right there. When we looked into it, we found that we had changed our stretch wrap, and it was too sensitive to summer temperatures, and it would shrink, like it would literally like shrink wrap against the pallet in between the cardboard layers. So it was out here and then it come back in. But what you see is like on the little bottles where the cardboard layers were very close together, it wasn't a problem because the cardboard kind of kept the stretch wrap away. But on these bigger ones, you know, the stretch wrap had plenty of room to go against the corner and dent the bottle. The project testing was completed in the winter, right? If I ask why again, it's okay, well, this is the reason. Okay, well, why did we implement the stretch wrap? It didn't work. Well, the project testing was completed in the winter, so there wasn't year-round conditions to test it on it. And it's not something that the project team came up with at the time. So overall, they ended up decreasing their wrapping tension in the summer, and then eventually we upgraded to a new stretch wrap material that wasn't so sensitive to temperature. Another example, recovering from a process upset. So I had out of specification material made, and there was a particular quality measure that was too high. So we understood what caused the issue, and we evaluated if mixing could be used to balance the material. So when I talk about math, pretty basic math here, right? I'm grabbing how much material I have. I just happen to measure it in inches, but it's essentially my volume. And then I have some quality parameter. And then if I sum it all up and essentially do a weighted average, it tells me that my final quality, when I mix the 19, the 4.5, and the 2 at these different volumes, is going to be this, and my upper limit was 5, which means that this was good to go. So I knew that if I produced at least 265 inches, that I would be in spec. And then with that, other skills was to be able to look at all these charts and data and analyze and understand what happened throughout the production. To fix the issue, we tracked additional set points in our production system and created some interlocks that if those set points were out, we weren't able to make the product anymore. And then it prevented us from making out of spec product. And we did end up using the mixing matrix to get rid of all of the out of spec material. Another example, system design. We couldn't get enough cooling and it kept shutting down our product because the temperature was too high because this particular material was too hot. So we inspected all the equipment, we inspected all the set points, center lines, and we found that the heat exchanger that we had designed, like that was in the system, was not transferring as much heat as expected. So what we looked into is after checking everything, we said, hey, gotta open up the heat exchanger because there's something wrong inside of it that we can't see. And what we found is that the chilled water side of the heat exchanger, so the way it works is it has a hot side and a cold side, and the chilled water is cooling my product, was contaminated. And you can see the plate right there. It's supposed to be metal. That's contamination. So we found that there was kind of an insufficient design in the system that would create excess contaminants to be built up. And then the heat exchanger was essentially filtering out the entire chilled water system. So we manually cleaned the heat exchanger. We made some upgrades to our chilled water system. Another example, some process improvements. So our daily cleaning cycle and the equipment is rushed, inadequate, and stressful. So we observed multiple cleaning cycles. We mapped the people movements and audited the tasks. So what you see on the top right is what it looked like before. It does look like a headless chicken running around the floor. And then we were able to optimize the task order, optimize material placement, eliminate, combine, and reduce tasks. And you can see what it looked like after. So a lot more, a lot more calm and easier to execute. And then the last example, some set point improvements we wanted to make. So we had a lot of stops in our case sealer equipment. The case is getting stuck on multiple parts of the machine, and we had to run 5 different case sizes. So we're constantly moving the machine to different points. So what we ended up doing is we measured cases, we measured the machine parts, and we understood where it was failing. And we actually created calculated set points for each machine area based on case size and machine components. So this is like where math came in, but to be honest, it's basic algebra. So I said, hey, what I can measure, what I can physically measure is from the top of the belt to the bottom of this roller. So I'm going to create a standard that says, hey, this is my case height, this is my roller height, this is my belt traction. And if I combine all of those things, if I measure this, this is how long I need that datum to be, that length to be. So now I was able to say, all right, for every single case size, if my case is this high, this is what I need the machine to be. And we were able to create that correlation. So then we could automatically calculate for any piece of corrugate what the set point should be. So those are all of my examples. And yes, some a little bit more technical than others, but again, it's all about problem solving. But the other thing I want to mention is don't forget about the soft skills. Things like being able to communicate, taking feedback, being able to collaborate, prioritize, and 80-20, right? Realizing that 20% of your effort gets 80% of your results. And yes, we always want to drive rigor, but understanding that in life and definitely at work, not everything has to be perfect. And knowing when it's okay to say, hey, this is good enough and this meets the intent and I'm okay to move forward. It's definitely a skill that we always have to teach because folks are so used to delivering things to 100% at school, which is, again, builds another set of really good skills with being rigorous. But it's also good to know when it's good enough. And then finally, to end it on a fun note, another way to encourage folks to go into engineering and like things is just do demos. So surfactant is the key thing that goes into dish soap that makes it work as dish soap. So here's some pepper on top of some milk and a drop of Dawn from a toothpick, and you can see what the surfactant does. It grabs all that dirt and pushes it away from the dish soap so it can float in water and run away. And with that, that brings me to the end of my presentation, and I'm happy to answer any questions. I think I see some.
Yeah, I'll pop back on. Don't worry, you don't have to deal with the technical stuff. I'll pop back on and ask you the questions. Actually, super cool last sort of like demo because we have some high school students who are AP Physics students with their teacher watching. So that works out really well. I remember learning some of that in terms of like kind of chemistry. And I was just, the physics and chemistry of that combined, I think are fascinating. Oh, okay, so from our physics teachers, did you take AP Physics in high school?
Yep, so I took AP Physics and I took AP Calculus. However, I retook Calculus in college. I technically didn't have to, but they said, hey, math is really important. We want you to have a strong foundation. So unless you're like extremely comfortable with it, we suggest you retake Calc, and I'm super glad I did. And yeah, and I loved my physics teacher. He happened to be an ex-engineer from the University of Illinois. So we had a similar background, but yeah, AP Physics and AP Calculus were really good foundations. And then yeah, the other APs I took were not math or science. I took AP Statistics. So AP Statistics was the other one. Yeah, and that really is a good one because you can see some of what I do is trying to combine things and figure out, hey, how likely is something to happen? What's my risk? And it's good to understand statistics from that perspective.
Another vote for physics on my end. Physics is really where I learned how, like, I have a degree in biochemistry, never used it because didn't know what to do with it. But I was the first time I really understood what science was.
Yeah.
And kind of like that repetitive process and how to apply, those equations to things and how to figure things out in a way that biology and chemistry didn't quite teach me in high school.
Yeah.
So you guys are well prepared for college.
Yeah, I know it worked out. And just kind of reading some of these other questions, somebody asked, like, what's the hardest math? To be honest, it was calculus. I really struggled with it. I had a good foundation in high school, and then in college I struggled, but luckily was able to really leverage teaching assistants and office hours and things like that. And I remember, tutors is the word I couldn't think of earlier. We had like free tutoring programs at the University of Illinois, so I used those a ton. And I'll honestly tell you that for a second, I thought I didn't like math because I loved it in high school, and then it got hard enough in college, and I was struggling. But I just needed to figure out how to study a little bit differently. And luckily I was able to learn through that, and it worked out really well. And I got through all of my math curriculum. I will honestly tell you, math were my worst grades in all of my college career. I did well in the science, and I did well on some of those advanced technical classes that teach you more of the engineering foundations. So it's a mixed bag of everything, and you really can put the effort, use resources, and learn it.
Also, what's the hardest math you do at your job then?
Algebra and geometry.
But it's good when you have to combine those two things. It gets kind of hard. Another question, what was your favorite subject in high school?
It was math. I will be honest, it's math, and I loved physics, which I think is part of the reason I went mechanical engineering as well, because of the physics side of it.
Awesome. Actually, I think this will be a really good last question. Is what was most surprising to you? Kind of when you started out, like, because you said you started with internships, like you got into the workforce and started applying, your educational background. What was most surprising to you?
Yeah. What was most surprising to me is what really mattered were my foundations as to like my basics of what I understood in math and science to be the fundamentals. And then from there, it was about my ability to combine information and combine skills, and really more use soft skills to get things done. So if anything, what surprised me is that I have never used differential equations in my job. I will tell you, the one time I used calculus is that I had a flow, and I wanted to know how much total flow we had. And I'm like, oh, that's technically an integral, right? But I didn't do an integral. I just grabbed every flow point I had and multiplied it times 1 second. So the concept was an integral, but I didn't actually do an integral. But it was interesting to be like, oh, that's like what an integral is. That's the only time calculus has come up in my career. But you can see that my job is a little bit different. I know some engineers do a ton of math and a ton of technical science, but I'm in a very much like a problem solving environment. So it's about combining a set of skills, combining the information that you have, realizing, for that heat exchanger, fundamentally, if my input temperature is the same, and my fluids haven't changed, and I'm not getting the same output, something's wrong in the heat exchanger, right? Like foundationally, that was like a simpler concept. Like if nothing else has changed, this one must have changed, right? And really being able to think through that and put those things together. So the theory helps, and having a really technical education helps because your foundations are so strong. But then really when it comes to the work day to day, it's your ability to use those foundations to then prioritize, make decisions, evaluate risk, be willing to try things and problem solve and those things. Yeah.
Awesome. And actually, since we have a high school class joining us, I'll ask the last question, which what's your best advice that you can give to high school students?
Yeah, the number one advice I'd give is Don't be afraid to try new things. Don't be afraid to explore. Leverage extracurricular activities, especially as you get into college. I got involved in Society of Women Engineers, American Society of Mechanical Engineers. I became an engineering tour guide, like really just trying to see what things were fun, came natural to me. Don't be afraid to don't put yourself in a box. Like for a second, I was like, well, I want to manufacture airplanes, so I'm going to become an aerospace engineer. Then I realized, I'm like, well, what if one day I don't want to manufacture airplanes? I realized like that was my only passion on the aerospace side, so maybe I needed to go somewhere else. So think about what makes sense to you. And yeah, engineering is just a phenomenal career to go into with an incredible amount of opportunity. So as you're in high school, focus on your strong foundations, but also realize that the soft skills are really important. Your ability to collaborate, having just general knowledge of what you're interested and passionate about is really important too. So you can make good decisions going to college. And as you get into college, really do things outside the classroom, get your hands dirty so that you also know what makes sense for you, what you want to go into. And internships are always a good idea. The earlier, the better.
Awesome. Thank you so much, Val. I'm actually really thrilled. That was one of the best explanations of kind of like the connection between the engineering, like, you know, kind of degrees and like the manufacturing portion of things. Awesome. So thank you very much. It was fabulous.
So just an agenda, I want to go through some personal education experience, a little bit about Equitrans Midstream, who I work for, what we do. STEM at Equitrans Midstream, I took a little different approach from Val, and I do have a lot of some info on engineering, but also some info on some technical stuff, some science that maybe you don't have to have an engineering degree for. And then some focus area for student development. A lot of what Val's already hit on, honestly. Okay, so personally, I went to Ripley High School in Ripley, West Virginia. I think maybe some of you on here are from West Virginia. I then went to West Virginia Institute of Technology in Montgomery, West Virginia, and received a Bachelor of Science in Electrical Engineering in 1994. And then went on to University of Texas at Dallas in Richardson, just outside of Dallas, Texas, and got my MBA in 2000. So from a work standpoint, I spent a little over 21 years in design engineering and management and telecommunications. So I originally went to work right out of college in 1994 as a field engineer for MCI WorldCom. A lot of you on here probably never even heard of that. But I started as a field engineer, then became a design engineer, got promoted into management, and then on up through management. And as you can see, I worked there for about 9 or 10 years. Very good company. I then decided to move back to West Virginia. I'd spent some time in Chicago with MCI WorldCom. Then I spent 7 years in Dallas, Texas with MCI WorldCom. Decided to move back to West Virginia, went to work for Verizon, who was later purchased by Frontier Communications, and worked there from 2003 to 2015. Started out as a director of engineering, got promoted to vice president. When I left there, I was the vice president of engineering and construction for the Eastern U.S. Since then, I moved to Pittsburgh, Pennsylvania in 2015. So I've spent 7 years in engineering management in the natural gas industry. I've worked for EQT, which is now Equitrans Midstream, for that entire time. So basically for 28 years, I've had a STEM-focused career. You know, what really drove me into STEM, into engineering in particular, was just curiosity. You know, when I was a kid, my dad just always tell me, Jason, everything you do, you want to try to, you know, anything toy you get, you take it apart and try to put it back together every time. So I just always had that curiosity and really not knowing much about what engineering was. You know, you all have people have a great opportunity now to listen to things like this and Google stuff on the internet. You know, when I was in high school, there was no internet, no public internet. People didn't have the internet. So, you know, we would go to career fairs, you'd talk to your guidance counselor, but it was all, you know, looking in libraries, talking to people. And I didn't have a really good feel for what an engineer was, but I thought that's what I wanted to do because I was really curious and interested in how do things work? How do you make things work? How do you make things better? So it turned out really well for me. I've had a great career in engineering. I love it. So a little bit about Equitrans Midstream. A lot of colored lines over there, and I'll go through a little bit of this. But we are headquartered in Canonsburg, Pennsylvania, which is just south of downtown Pittsburgh. We're a 135-year-old company. We focus on sustainability. It's a big thing in the world today with emissions and stuff like that. We have a large focus on methane reduction, emission reductions, carbon neutral, things like that. We have 750 plus employees. We have 1,900 plus miles of gathering pipeline. We have 750 miles of regulated transmission pipeline, and I can go into a little bit about what that means in a second. We have 580,000 horsepower of compression where we compress natural gas. And on a daily basis, we transport 8.2 billion cubic feet of natural gas. We also have 180 plus miles of water pipelines. And basically what those water lines do, you probably are thinking, why in the world do you need a water line in the gas industry? We provide water to the wells that they utilize to drill the wells with. So, basically in the natural gas industry, there are three kind of divisions of it. There's what's called the upstream, the midstream, and the downstream. So the upstream are the wells, the gas wells that are drilled. My company doesn't have anything to do with that. The midstream is what we do. So we build pipelines and compressor stations, and we interconnect with the production companies that drill the wells, and then we transport the gas from the well pad to the downstream companies. The downstream companies are people like, in this area, People's Natural Gas, Dominion Gas, Mountaineer Gas. For you all out in California, People's Gas and Electric. Basically, that's the natural gas line going to your house. So we call that the distribution company. They distribute the gas to the end user, which are either businesses or houses. And then I can't go on without saying safety above all else, and a commitment to responsible operations that protect our employees, our contractors, and our communities. That is our one of our core values in our company is the safety and the protection of all of our assets, all of our people, all of our customers, anyone we interact with. So that's a little bit. If you look over here on the right on the screen here, you can see all these different colors. I just cut and pasted this out of one of our brochure kind of things, but you can see our interconnected pipelines and what we have. We don't have a very large footprint. You can see that Pittsburgh, Pennsylvania is right here in this mess right here. Actually, it's a little north of here. It's up here. But, we're basically in southwestern Pennsylvania, northern West Virginia, and then a little bit over here in eastern Ohio. With only 750 employees that we have, I didn't put this on here, but we're the third largest natural gas transportation company in the United States. So what does STEM mean to us? Like, what do we do? How do we apply STEM? So like I said at the beginning, I want to talk a little bit about the non-engineering piece of STEM. The science, the technology. So, we have, I listed a few out here. We have operators that work on our equipment, work on our pipelines. And what do? They maintain our assets so that they safely operate. They're very hands-on, mechanical. The majority of their time is out in the field. So I've got a picture right here. This is a compressor station where we compress the gas and move it on down the pipeline. This right here is a 5,000 horsepower Caterpillar engine right here, driving a centrifugal compressor. You can see it has these ends on here. There's 3 on each side. It's called a 6-throw compressor. And basically what we do is the gas comes into this station, and basically it's at a certain pressure, and to transport it, to move it on, you compress that gas to increase the pressure, which increases the flow. So, a prime example of what we would do here is we would have gas coming into this compressor at 300 pounds per square inch, or PSI. We would compress it up to 1,200 pounds per square inch, and then move it on down the line to the next compressor station. And in between, we may have interconnects with some of the distribution companies where we're selling them gas that then goes to your house, your business, etc. Run your furnace, your cook stove, so on. Technicians, that's another title that we have. Again, they maintain our assets that safely operate. They do a lot of troubleshooting, right? If gas isn't moving right, if we're seeing errors in our control room and it looks like we may have a valve that's stuck, a technician will go out there, troubleshoot, work on that valve. They develop set points, right, to look at pressures and flow rates throughout our entire network. The engineer will design what that equipment would be and what the set points should do, but the technicians will go out there and actually set those set points and say, without getting too technical, then you won't know what I'm talking about, but like a pipeline, for example, the pipeline's rated for so much pressure. Say it's rated for 1,400 pounds. If we would have a valve stick open and we would go to overpressure that pipe, as it reaches that 1,400 pound set point, we have relief valves on that pipe. So it won't allow the pipe to overpressure. It'll relieve gas to atmosphere and alert us. So our technicians would go out and set all those set points. The operators would go and troubleshoot if there's a problem. And then lastly, in the office setting, we have our IT group, right? We have a very vast control room, very complex control room that monitors our assets across the footprint, looking at flow rates, looking at design points, looking at pressures. And our IT group kind of oversees all that. And then obviously engineering. So just a little focus on the engineering to break out the E in STEM I've highlighted here. Again, like Val said, you would think, Val would probably think with her background in mechanical engineering, oh, the majority of these engineers are mechanical engineers. Not true. Just like she told you, every engineering discipline we utilize. So mechanical isn't obvious, I agree. They do pump designs, motor designs, valve designs, the pipeline design. They run calculations and determine based on, our customer needs X number of cubic feet delivered to an endpoint. A pipeline engineer who's typically a mechanical engineer will determine what size pipe do I need to transport that much gas at that pressure. What does the wall thickness of that pipe need to be so that it can safely operate? Where do I need relief valves that I talked about earlier? Things like that. Electrical engineers, we have a lot of electrical engineers, I'm one of them, but they do the power design. So you think about that compressor station I showed you a picture of, there's a lot of electrical power required for that. So our electrical engineers design all of our power for all of our sites. They design the communications, right? I told you all I spent 21 years in telecommunications. That was it's still applicable to what I do today. We have to have connectivity, fiber optic connectivity between all of our sites so we can monitor and watch and all the gas flow. Automation and control. That is a very interesting field, in my opinion. If I had to do over with, I probably would go into automation and control, to be honest with you. So what that involves is controlling a system. Take a compressor station, for example. They will come up with the documentation and the design that says, at this set point, at this pressure, open this valve. If you pressure drops below this point, then automatically close this valve. They do all the design of that. Very interesting stuff. Chemical engineers, they do process design. Val did an outstanding job at explaining process design, but within the natural gas industry, we have a lot of processes that they design. They do liquids modeling. Natural gas there's a lot of temperature dependencies to it. And some of the basic math around natural gas is as you cut pressure, the temperature cuts with that. So for every 100 pounds of pressure drop you have, you lose 7 degrees Fahrenheit in temperature. So as you can imagine, if we've got a location like, let me back up a step. The gas coming to your house is under 100 pounds, 100 PSI, pounds per square inch. Because the piping within your house, the plastic, that's all that can withstand. Your stove in your house, that's what it requires, is a lower pressure gas. So we're transporting this gas at high pressure so that we can move it along for greater distances. And then when we get to a point where we go to a distribution company where we're cutting the pressure, you can imagine, say if I cut from 1,400 pounds to 100 pounds, that's 1,300 pounds times 7 degrees Fahrenheit per pound, whatever that math is, 80 some pounds, right? 80 some degrees you're dropping. So if you start out with 50 degree Fahrenheit gas, now all of a sudden you have negative 30 degree Fahrenheit gas. Any water that's in that gas, which natural gas naturally has water in it out of the ground, can freeze. So our chemical engineers, they determine where do we need to add heat? Where do we need to add line heaters to heat the gas so that we don't have freeze-offs? And then finally, civil engineers. As we're building pipelines, especially in this part of Appalachia, there's a lot of hills up and down, rugged terrain. Our civil engineers, they look at landslide remediation. They proactively try to, as we're building pipelines, they will proactively talk with our construction team on here's what you need to do with the soil so you don't have landslides. They'll design all of our site plan, our site development, right? If we're building a compressor station, then they'll lay out all of the earthwork design, what the cut fill is on the site, where the heavy equipment operators and what they need to grade the slope to. And then also erosion and settlement control plans. So as we're building pipelines, we've got to make sure that any water runoff, because we've eliminated some trees, we've got to make sure any water runoff doesn't cause flooding, doesn't get into local streams, etc. So they'll design those erosion and settlement control plans. All right, so some of the STEM ideas for teachers, continue focusing on math. Telecom and natural gas have math as a basis. Encourage students to take advanced math and science courses, especially ones that want to go into a STEM career. That is the basis for engineering. Another idea I had, and I'm sure a lot of the teachers are doing this, but partner with companies like Equitrans Midstream and like Procter & Gamble, different STEM industries, for mentorships, real world projects. If we had a class that wanted to look at a compressor station design, we would work on that with you, quite honestly. And even potentially some funding. We partner with a lot of education facilities or county educations in West Virginia, different county and local school districts in Pennsylvania and Ohio. We partner with them and help them financially with some funding. And then the last thing I have on here is the same thing that Val said. Critical thinking and collaboration are key. Engineering is not all about math and science, which I say at the top here, it is. But to be a successful engineer, you've got to have critical thinking. You've got to be able to collaborate. You can't just be what I would call book smart, right? There's a lot more to being a successful engineer than just knowing calculus 3 and differential equations and and all these advanced courses. To be successful, you've got to really be good at critical thinking, collaboration, problem solving, so on. That's all the slides I have, but I do have one show and tell that I wanted to show you all. This is, and I'm going to hold it up here. I'm hoping it works. Would anybody have a clue what I'm holding up right now? All right. So what this is a cutout of a piece of high density polyethylene pipe, HDPE pipe. So we've recently had some failures on some pipes. So this is a really good thing about what engineers do, right? So we have been working and trying to determine why is our pipe failing. So I took this pipe to a lab last week, ran some tests on it, and I'll show you what we did. So it's hard to imagine, but the pipe, this was cut out of a circular piece of 18-inch pipe. And what we did was, I'm going to put my finger in. When you have HDPE pipe, you fuse it together. Instead of welding like you'd weld a steel pipe, you melt and fuse this plastic pipe together. So what this is right here where my finger is, this is the fuse right here. And the rest of it was just a chunk like this right here, all the way across. And what we did was we put this piece into it's called a tensile test. We put this piece in there like this through these two holes. We drilled these two holes in it, put it in the machine, and we pulled it apart. So basically this is going to prove whether our craftsmanship on making fuses is good or not. If our fuse was not good, this would have popped in two right here. If the fuse is good, the fuse should be stronger than the base material, which is the HDPE pipe. And as we apply pressure and pull it apart, it should just stretch this like Laffy Taffy or like Play-Doh. And sure enough, as you can see right here, it stretched the material. It was almost to the point of breaking and we stopped. You can see a hole in it. But what we proved there was our problem with our recent failures we've had is not our fusing techniques, which a lot of people thought was the problem. We proved that our fuse is accurate. Now, what is our problem? We're still looking into it. I don't have the answer. You have to come back next time. But what we did prove was we disproved the fact that a lot of people thought it was our fusing and our human, technicians out there doing the fusing. It wasn't. The fuse was perfect. All right. Any questions now?
Yeah, we do have some questions. And actually, let me see if I can get a different view here. All right, that's better. So yeah, actually, and I'll be honest with you, some of these other questions that we had earlier are great questions. So let's start with real quick. What was your favorite subject in high school?
Again, it would be math. That was my favorite thing, and I enjoyed it the most, and I did the best in it. So math was my favorite subject.
What do you like most about being an engineer?
I think solving problems. That's the best thing, and you get to see an end result, right? A problem is presented to you, then you take the necessary steps, whether they be simple, complex, short, long, whatever, and then in the end, you solve that problem. That's probably the best thing about being an engineer, in my opinion.
Well, I guess, because I think this is kind of interesting, we're on a math trend today. So what's the hardest math you do at your job?
Probably like, same thing as Val said, probably algebra and geometry, quite honestly. Now, there are some more advanced things in the design of pipelines that takes calculus into account, but we don't have to do it by hand. We buy software that does it for us. So, right, we put the parameters in of, we want to move this much gas at this pressure. It runs it all in the background, and it comes back and tells us the result. And there is calculus and a lot of advanced math in it, but my engineers don't do that by
Awesome. No, I think it's really encouraging for students to realize that, like, and I think some of it is like the calculus helps you think about like how the math is related to itself in some ways. You know, because I always thought that was really interesting with calculus, and gets you to think a little bit. But you're not like sitting there solving calculus problems all the time. And I guess, what does a day in your life at work look like?
So a day in my life, it's a little different in that I manage people. So the majority of my time I'm in meetings. So I spend a long time looking at budgets, right? Where are we at on this project? Doing readouts of, the budget was this. We're 90% complete of the work, but we're 95% of the budget spent, analyzing that, et cetera. But I'll answer maybe more of the engineers that work for me, a day in their life. They are assigned projects, whether it be pipeline, compressor station, or whatever. And basically they take the inputs, the required scope of the project, what does a customer need, and then they design a solution, whether it be the size of the pipe, the length of the pipe, the pressure of the pipe. They design a solution that meets the customer's needs. And it's a lot of detailed design, detailed engineering analysis is what they do. It's definitely an engineer job.
Yeah. So then I guess a different question though, in terms of your career, is how has your engineering background prepared you kind of to take on some of this management stuff that you're doing?
Great question. So I think there's two things. One, I started off as a field engineer, and I tell people this, I've been telling people this for 28 years. A fresh engineer out of college, I think the best thing they can do is get a hands-on job, whether it be in manufacturing, whether it be in telecom, whatever industry it is. I spent my first about 2 years as a field engineer, and I really got to the ability or the understanding of the technical aspects of how things work. And then when I went to the office and into an office setting as a design engineer, I had that technical fundamental background of how it worked. And that led me to be kind of a top candidate for management if I wanted to go that route, because I had that firm understanding. And then the other thing I did, if you remember on my experience there, I did go get an MBA pretty quickly out of college, well, within 5 years out of college. And that helped me also in the management.
Awesome. That's actually a really interesting answer. I had someone else who kind of talked us through the different stages of an engineering career, because he had just started the middle of his career and kind of getting into some management. And it was just really interesting to hear how that kind of transitions and transforms. Yep. And my last question, because I think this is always a good one, is what's your best advice for students who might be interested in engineering or natural gas?
I think, continue to take technical classes in high school. And then I really like Val's answer, right? In that, get involved in other things. Don't just study in books, right? Do some hands-on things. Get involved. My son, for example, he is a junior mechanical engineering student at the University of Tennessee in Knoxville. But when he was in high school, he was in the STEM program in high school and did robotics. He did all these different things, and it really, really broadened his horizon and his knowledge base. So I would recommend just, obviously continue studying hard, really focus on the math, the advanced math, advanced science classes, but don't just do the book work, right? Get involved and learn other things too. It'll really help you.
Awesome. And that is all the time we have. I want to thank you so much for presenting tonight.